Good morning, everyone. So let me share my screen because I can do that. Good. So we'll start off with a couple of reminders. So don't forget, exam number 4 is coming up already. So it's not this Friday, but it is next Friday. Remember, we basically have an exam every 3 weeks. So exam number 4 is going to cover the things that we're talking about now. So basically magnetic force and magnetic fields. And then what we're going to do in the next chapter, which we'll probably start that next chapter tomorrow. So we'll finish off most of this chapter today, if not all of it today. Some announcements. I'll post the exam 4 examples after class today. And then I will also post the extra credits probably today or tomorrow, the outside extra credits. But that won't be, you probably won't be able to do that yet because it'll involve stuff from next chapter. So, but I'll post it anyway so you can kind of start looking at it. So good. So kind of a quick reminder what we talked about yesterday. I'm gonna move our faces down here. 2 days ago. There you go. 2 days ago, we talked about Ampere's law. So remember, Ampere's law is the magnetic equivalent of Gauss's law because Gauss's law doesn't actually work for us. So this is the magnetic equivalent. Oh, if I know how to spell equivalent of Gauss's law, right? Because again, Gauss's law always says that the magnetic flux will be equal to 0, which isn't exactly useful when we're trying to figure out the magnetic field. So we had to use the fact that the magnetic field curls around in a circle. So in this case, we're going to do a closed loop integral. So we integrate over the perimeter of some two-dimensional object, usually some sort of planar object. So that's what the left-hand side is. And then the right-hand side is mu naught times I enclosed, where I enclosed is the current which is contained within inside of that closed loop that we draw. Right? Same thing as Gauss's law, where Q enclosed was simply equal to the charge which was enclosed in there. So in a general case where the current density is non-constant, in that case, I enclosed is simply going to be the integral over the current density integrated over the area, where again, the current density is equal to the total current divided by the total area by definition. And then if we're dealing with something which is a cylindrical wire, in this case, dA is equal to 2 pi r dr. So this is our dA. Okay, so this is what we talked about last time. So we did a bunch of applications of that. So we're going to finish off Ampere's law by doing another application of Ampere's law. And this application is what's known as a solenoid. So solenoids in magnetism are very important. So this is a very important quantity that we do in magnetism, which is going to start showing up in circuits. Okay. So we're going to take these guys, we're going to put these in circuits, and these are, as it turns out, the magnetic equivalent of a capacitor. So if you remember what a capacitor was used for, anybody remember what a capacitor was used for?
Charge.
Good. To build up charge to store energy for later use. Exactly. So what the solenoid is going to do, so let me tell you what a solenoid is. So a solenoid is, it is simply a coil of wire. So this is our solenoid that we're then going to run a current through. Okay. So I'm going to run a current through this solenoid. And what will happen is, as you'll kind of find out next chapter when we start talking about this, it takes a while for the current to actually build up inside of the solenoid. And we'll talk about why that happens next chapter. But basically, you have to do work to overcome what's called a back current inside of this, which means that it takes work to actually cause this thing to fully charge up with current, which means the purpose of putting in a solenoid inside of a circuit is to do the same thing as a capacitor, which is store energy for later use. Okay. But for now, let's just talk about what a solenoid is. So again, a solenoid is a coil of wire. So these have n number of coils. So inside of here, I have n number of coils. N is equal to the number of coils, where each one of these coils is supposedly, doesn't have to, but basically has roughly the same cross-sectional area. So if I looked at it, so this is my side view. If I looked at it from a front view, this thing would basically typically just be a circle of some radius of r. And so it's going to have a radius capital R. So this is our front view. And let's say, just for funsies, that my current is going in this direction. So it's going in a counterclockwise direction. So if I was looking at it from the front, so let's say my eye is here, and I'm looking at this guy. So what I'm seeing here then is the cross-sectional area from the front, and I'm seeing the current is actually going in a counterclockwise type direction. Okay. So since we're using Ampere's law, what we want to know then is what is the magnetic field of this solenoid as it has currents running through it. So what we want to know for this particular problem is what is the magnetic field of the solenoid? Right? So I want to know what is this guy. Okay. So to do this, let's imagine that we have this coil, but we're going to cut down through the center of the coil. Okay, so if I go back to my previous slide, so imagine that my coil again is running in this type of direction. I'm going to take a knife and chop through the center and look at basically the cross-sectional area of it. Okay, so this is what we kind of want to look like. So what that means then is I'm going to have some wires here. Then I'm going to have other wires here. So these are the cross sections of the coils. Right? So here I said I have current going in a counterclockwise direction. So what's happening is what on the top ones, I have currents coming out. So current is coming out through each one of these guys. And then it's going in through the bottom ones. Okay. So down here I have currents coming in. Now, since all of this is connected to the same object, what that means is that each one of these currents is exactly the same. So the current coming through each one is simply I, right, which is the current which is running through the entire solenoid. So before we apply Ampere's law, let's think about what the magnetic field is actually doing. So let's draw the magnetic field for each one of these different wires. So again, if I'm looking at this cross section here, I have current coming out at me. So right hand rule number 1 says I put my thumb in my direction of the current, my fingers curl around in the direction of the magnetic field, which in this case means that my magnetic field is curling around in the counterclockwise direction. So for all these ones on top, my magnetic field is curling around in the counterclockwise direction. So that's each one of these guys, right? So this is my B field. For the bottom one, my current is going in, so I put my thumb in the direction of the current, curl my fingers around in the direction of the magnetic field, which means that down on the bottom, my magnetic field then has to be going in the clockwise direction. So I'm gonna draw these guys in yellow. So all these ones then have magnetic field going this way. So clockwise. Now again, I'm drawing a small section of this. So what we're imagining here is that our solenoid is actually infinite in length. Okay, so we're pretending that our solenoid is infinite in extent. If it's not, then what we do here is only true in a small section where we can approximate it to be that way. So infinite in extent. So let's start looking at the superposition of these magnetic fields. Okay, so basically what's going to happen is if I follow this one around at the center point between these two magnetic fields here, or at least between these two wires, this one is curling around in the counterclockwise direction, which means that this middle part, this one from the left, is then pointing straight up. So this is the magnetic field from the left-hand side. The one from the right-hand side, this one is also curling around in the counterclockwise direction. But by the time I get to this point, I take the tangential direction in which it's moving, which means this guy is actually moving downward. So the magnetic field from the right is then downward. Right? So the superposition of these two fields, since they're both exactly the same distance away, that means this portion of the field will actually cancel this portion of the field. And the same thing is going to be true here and here as well. So anywhere in between these portions of wires, the magnetic field is actually going to go to 0. So there's going to be no portion of magnetic field between the wires. Down here, it's going to be exactly the same thing. So here, my magnetic field is going in this direction. So from the left-hand side, this one is going to point downward. So this is going to be B left on this side. This one, B right, is going to point upward. So again, these guys are actually going to sum together, which means that, again, there's going to be no vertical portions of magnetic field, at least between the wires. Now let's look what happens on the inside. For the inside portion, if I look at along this line across here, at this bottom part here, if I look at, say, this guy, get away from these, magnetic field is curled around in this direction. So at this point, I would take the tangential projection. So my magnetic field from the top is going to point in this direction. And from the bottom one, magnetic field is curling around in this direction. So a tangential direction of this guy is going to be in this direction. So in between the wires, basically what's going to happen is that what? The superposition of the magnetic fields then is going to kill off all vertical portions of the magnetic field. So the magnetic field then will only point along the axis then of the solenoid. Okay? So my total magnetic field for my solenoid is going to point only along the axis in this direction. So this is going to be my B solenoid. So anywhere on the inside, it's pointing, in this case, to the right. Now, what happens on the outside? Well, on the outside, what's happening is what? This portion, magnetic field is pointing this way. But from this wire down here, the magnetic field up here will be pointing in this direction, which means that outside of the wire, what will happen is I'm going to get a superposition of the magnetic fields, again, in the opposite direction, which means on the outside of the solenoid, as long as my solenoid is infinite in extent, the magnetic field on the exterior is going to be 0. Right? So the only magnetic field that is going to exist inside of the solenoid will point along the axis of the solenoid, all in one particular direction. There's no vertical portions. It's only going to point along the axis, so nothing perpendicular to the axis. And again, as long as this guy is infinite in extent, then the magnetic field outside is going to be equal to 0. Now, if you think about the parallel plate capacitor, this is exactly the same thing we found in a parallel plate capacitor. So the parallel plate capacitor, if I had this guy, so let's draw him. What we found here was that the electric field on the outside was equal to 0. And on the inside, if say this was the positive plate and this was the negative plate, then my electric field only pointed from the one plate to the other plate, and this guy was simply equal to a constant, where that constant then was equal to eta divided by epsilon naught. So here, the electric field pointed perpendicular to the plates, only pointed in one direction, and it was 0 on the outside. So my solenoid looks something very, very similar to this guy. Okay. Now, to determine the magnetic field, let's now apply Ampere's law. So let me start a new page. Let me redraw what's going on here. So again, what's happening here is, let's say here's the cross section of my wires. Here's my wires. Okay. And we now know the magnetic field only points in this direction. So here's my magnetic field. Good. So now let's apply Ampere's law. So here, for Ampere's law, I'm going to choose a loop that does something like this. So I'm going to draw a rectangular loop. So here's my rectangular loop. I'm going to call this point here A, this point B, this point C, and then this point D. Right. So in this case, I'm going to integrate along my closed loop in the counterclockwise direction. Okay, so I'm going to integrate along it in this direction. So left-hand side of Ampere's law then says that the closed loop integral of the integral dotted by the differential length is then going to be broken up into 4 different integrals. Right? I'm going to have the integral from A to B, integral from B to C, integral from C to D, and then the integral from D to A. So the closed loop integral is simply the sum over all 4 of those integrals. So this is going to be equal to the integral from A to B, the magnetic field dotted by the differential length, plus the integral from B to C, the magnetic field dotted by the differential length, plus the integral from C to D, the magnetic field dotted by the differential length, and then finally plus the integral from D to A of the magnetic field dotted by the differential length. Okay. Now, let's talk about each one of these integrals. So from B to C, DL then is going perpendicular to the direction of the magnetic field, which means my magnetic field is pointing to the right. DL is going vertical, which means that I have an angle of 90 degrees between B and DL. But what's the integral of B dot DL if these guys are perpendicular to each other? So if these two are 90 degrees from each other, so remember B dot DL is the same thing as B times DL times cosine of the angle between the two. But if the angle is 90 degrees, what's cosine of 90 degrees?
0.
0, good. So this one is automatically 0, right? Because here DL is perpendicular to the magnetic field, so this guy has to be 0. Going from D to A is exactly the same thing. So what's happening here again is that the magnetic field points this way. DL points downward in the perpendicular direction, which means these guys are perpendicular to each other. So this guy is also equal to 0. In the section then from C to D, we just argued that the magnetic field out here must be equal to 0. So here, this portion is also equal to 0 because the magnetic field is equal to 0. Okay. So here, this one's 0 because the angle is 90 degrees. This one's 0 because the angle is 90 degrees. And this one is 0 since the magnetic field itself is equal to 0. Which means, along this closed loop integral, the only portion which is going to be non-zero is the portion from A to B, which I'm then integrating along since that's the portion which is parallel to the magnetic field itself. Which means that this thing becomes simply equal to the integral from A to B of then what? B times dl. Because here I'm taking the dot product is 0 degrees, and we're this section here. So cosine of 0 is simply equal to 1. Now, everywhere along this line, I didn't really draw everything kind of parallel like I should have, but since this line is parallel with the magnetic field, it means that the magnetic field is constant along this line, so I can pull that outside of the integral. So this becomes B integral from A to B of dl, which is simply just equal to B times L. So here I'm saying that the length going from A to B is simply equal to L. Okay. So this section here has a length of L. Okay. So my left-hand side of Ampere's law simply says that what? The closed loop integral is the same thing as simply B times the length of this section that I drew. Okay. Now, what about the right-hand side? So the right-hand side says we have mu naught times I enclosed. Well, what's I enclosed? Here, I enclosed then is simply equal to the number of coils that I'm enclosing inside of my loop times the current I, since each one of these loops has exactly the same amount of current. Okay. So that means the right-hand side then is simply equal to mu naught n times I, where n is the number of coils that I have enclosed. So if I put both of these things together, what this says then is that the closed loop integral of B dot dl equal to mu naught times I enclosed is B times L is then equal to mu naught times Ni, which means the magnetic field then of the solenoid is simply equal to mu naught N times I divided by L. Okay, this is our magnetic field. Typically from here, we're going to define a new n. I'm going to call this little n, which is equal to big N divided by L. So this is equal to the number of loops per unit length. So this is little l. So little l then has units of what? Number of loops per length. So this has units of 1 over meters. Okay. So written in this form, then the magnetic field of the solenoid simply is equal to mu naught little n times I. So this is my magnetic field of my solenoid. Okay. Now notice this guy, just like the electric field for a parallel plate capacitor, which again is equal to eta divided by epsilon naught, this guy is simply equal to a constant. Because here, nothing here depends on anything which is spatial. Mu naught's a constant, n is also a constant, that's the number of loops per unit length. I is a constant, that's the current that I put through it. So everything here is actually simply a constant value, just like that of the parallel plate capacitor, where the electric field was constant. Here, the magnetic field is also constant. So my magnetic field is constant and points along the axis of my solenoid. So good. So if I go back, once this thing goes away, good, and I look at my front view again, in this case, my magnetic field will point in this direction. Okay. This is given by then right-hand rule number 3. So remember, right-hand rule number 3 is we curl our fingers around in the direction of the current. Our thumb then points in the direction of the magnetic moment, or the direction of the area, which in this case is in the direction of the magnetic field. So right-hand rule number 3 then tells me the direction at which the magnetic field points. So again, for a solenoid, our solenoid then has a constant magnetic field, which is simply equal to mu naught times n times I. And again, this thing points along the axis of the solenoid. Okay. Everybody's okay? Not too bad. So let's use this and let's do a quick example, a nice easy example. So this says we have a solenoid that is 95 centimeters long and has a radius of 2 centimeters and a winding of 1,200 turns. So that's our N, capital N. It carries a current of 3.6 amps. And all it wants to know then is calculate the magnitude of the magnetic field inside of the solenoid. So this is a nice, very simple, very simple question. So again, what do we know? We know the magnetic field inside of the solenoid magnitude is equal to mu naught N times I, which is the same thing as mu naught capital N times I divided by L. Now here the problem tells us the radius, but we don't care because it actually doesn't depend on the radius. All it depends on is the number of turns, the length of it, and the current. So that means our magnetic field then is equal to mu naught, which is 4 pi times 10 to the minus 7, times our number of loops, which was 1,200, times our current, which our current was 3.6, and the length is 95 centimeters. So times 3.6 amps divided by 0.95 centimeters, or in this case, meters. So 0.95 meters. So plug all this into our calculator. In this case, what we find is that the magnetic field is 0.00571 Teslas. So this is the magnitude of our magnetic field through the axis of our solenoid. Is it breakfast time for the little guy, Derek?
Yeah, he just woke up.
Gotcha. Very nice. If it's anything like my children, it'll end up all over his face and the floor and everything else, so it'll be great. All right, everyone's okay? So not too bad. We'll do another example with this in a little while, but so these are solenoids. So again, the point of the solenoid is that the solenoid again is the magnet equivalent of the parallel plate capacitor or any capacitor. So we'll make more use of this next chapter when we see how that actually works. But again, they're going to be very important to us moving forward in magnetism, especially when we start putting them in circuits. All right, so good. So now what do we see? We have now seen force. So if I had the magnetic force on a charged particle, this was QV cross B. We had the force on a straight wire, which was equal to what? I times L cross B, or the force on a non-straight wire, which was the integral of I dL cross B. So this is where we started off. We saw all these different forces. And now what we know is actually how to calculate magnetic fields using either Biot-Savart's law, which says that the magnitude, so this is mu naught I over 4 pi integral of dl cross r hat divided by r squared, or now Ampere's law, which says that the closed loop integral of b dot dl is then equal to mu naught I enclosed. So basically what that means is now we know how to calculate the external magnetic field. We know the force then on a either charged particle or a wire which is carrying current. So now we can actually start putting both of these things together. So now we can start using these two things simultaneously to then determine what is the force on something due to something else where we have to calculate the magnetic field. So a good example of this is, what then is the force between two parallel wires? Two parallel wires. So basically what's going to happen here is we have a wire in an external magnetic field, but that external magnetic field is generated by another wire. So we want to know then, what is the force which each one of these wires is going to encounter? So, or how much force does each wire place onto each other? So let me draw two wires here. So these are going to be my two wires. Right. These guys are parallel. And basically we're going to have two different cases, right? So the first case is when both currents are, say, parallel, so they're going in exactly the same direction. So case number one is when the two currents are in same direction. And then case number two is when the two currents are going to be in opposite directions. We want to see what happens in these two different cases. Okay. So let's look at case one. So let me call this wire number one. So I'm going to say this guy has current I1 running through it. And just for funsies, I'm going to say each one of these guys has exactly the same length. Okay, so I'm going to call this guy length L, and this one has exactly the same amount of length L. And then this one is going to have a current I2, and we're going to look at case one. So we're going to say I2 points in this direction. Okay. So let's say what we want to know here then is what is the force on wire one by wire two? So let's look at the magnitude of this guy first. Okay, so let's look at its magnitude. So what is this guy equal to? Well, okay, so here we know that these are both straight wires. So this is going to be the current from wire one, since we're looking at wire one, times the length of wire one, right, which is L, times the magnetic field, which is the magnetic field from wire two, times sine of the angle between the two. So this is our force. Now, let's think about each one of these guys. So let's go back a slide. Said previous. There we go. Good. So let's think about each one. So this one has current going in this direction, and we want to know what is the direction of the magnetic field on wire one from wire two. So here again, we're going to use right hand rule number one. So right hand number one says we're going to put our thumb in the direction of the current. Our fingers are going to curl around in the direction of the magnetic field. So in this case, our magnetic field is going to curl around in this direction. Okay. So what that means is anywhere above wire two, the magnetic field then is going in. So this is B2. And anywhere below it, the magnetic field is coming out. Right? So this is B2. So let's look at this portion here. So what we care about, at least at this stage, we'll talk about the direction of the force in a second, is what's the angle between the current and the magnetic field. So in this case, my current is going to the left, my magnetic field is going into the board. So what's the angle between those two things?
90.
90, good. So in this case, the angle between the two is simply 90. So here we know that this is going to be theta equal to 90 degrees, which means that this guy is going to be equal to I1 times L times simply B2. But B2 is that from a straight wire, so we know B2 is going to be mu naught I2 divided by 2 pi d, where d in this case is the separation distance between the two wires. So this distance here is going to be the distance d. And we got this last time using Ohm's law, or not Ohm's law, sorry, Ampere's law. So put all this together, this becomes mu naught I1 times I2 times L, all divided by 2 pi d. So this is my force on wire one by wire two. Magnitude-wise anyways. Now, by exactly the same argument, we can say in this case then is that the force on wire two by wire one magnitude is then equal to what? I2 times L times B1 times sine of the angle between the two of those. Well, let's go back to our picture. What's the angle between those? Well, from wire one, again, our thumb would go in the direction of the current. Our fingers would curl around in the direction of the external of the magnetic field, which means for this guy, I have to use a different color. What color haven't I used yet? We use red. So for him, his magnetic field is going in the same direction as the other guy, which means that anywhere above him, his magnetic field is going inward. So this is B1, and anywhere down here, B1 is going in this direction. So again, the angle between the two is simply 90 degrees as it was before, which means that this guy then is going to be equal to, by exactly the same argument, mu naught I1 I2 times L, all divided by 2 pi d. So these two forces, as we can see from here, magnitude-wise are exactly the same. So that means that the force on 1 by 2 magnitude is exactly the same as the force on 2 by 1. So these guys are exactly the same magnitude of force. But what about the directions of the force? So let's talk about the directions of the force. So here, again, using this guy, we would then say the direction of the force on wire 1 then would be, we would point our fingers in the direction of current 1, curl our fingers then into the direction of magnetic field 2, and then our thumb would give the direction of the force. So in this case, my current is going in this direction. I'd have to curl towards the magnetic field, so I have to put my palm towards the direction of the page, curled towards magnetic field 2, which means the direction of the force on him is going to be down towards wire 2. Okay. So in this case, the force on 1 by 2 is in this direction. Okay. The force on 2 by 1, then, we'd have to do the same thing. So we put our fingers in the direction of the current. In this case, our magnetic field is outward, as we had drawn on the picture. So I have to rotate my palm this way, curl towards the external magnetic field. My thumb points direction upward, which means that the force on 2 by 1 is in this direction. So what this tells us then is what? Whenever the current is in the same direction, these guys are going to feel an attractive force. These guys will be attracted to each other, but they're attracted to each other in such a way that they abide by Newton's third law. The magnitude of the forces are exactly the same, but they have opposite directions. Right? So good. So from this, what we learn is for case 1, these guys are attracted to each other. Okay. So these guys are attracted to each other, and again, they abide by Ohm's or Newton's third law, which says that the force on 1 by 2 is equal to negative of the force on 2 by 1. So these guys are satisfying Newton's third law. Okay. So this is case number 1. Now let's look at case number 2. So case number 2, I'm going to draw my wires again. So here's my wire. Here's my wire. So I'm still going to choose I1 to go in this direction. So this is still I1, but now I'm going to have I2 go in the opposite direction. So this is now going to be I2. Okay. So let's now talk about direction of the magnetic field from 1. So again, from 1, we know it has to curl around in this direction, again, based off our right-hand rule. So B1 then is going to go in this direction. So this is B1, which means at wire 2, B2 is coming, or sorry, B1 is coming out of the page. So this is B1. Okay. For I2 is going in this direction. So magnetic field 2 is going to curl around in this direction. So it's going to curl around in the opposite direction. So this is going to be B2, which means that what? Up here at wire 2, B2 is coming out. Okay. Now notice that the magnitude of the forces stays exactly the same. All of this stuff is still true. The magnitude of the force on 1 by 2 is exactly still the same. The magnitude of the force on 2 by 1 is exactly the same. Nothing has changed. But what changes is now the directions. So let's look at the direction of the force on 1. So on 1, again, I point my fingers in the direction of the current, which is going in this direction. External magnetic field is pointing out, so I got to rotate my palm towards me, curl, which means that the direction of the force on 1 is actually now this way. Instead of towards it, it's actually away from it. And for 2, I pull my fingers in this direction. Magnetic field is out, so I got to rotate my palm this way, curl, so my thumb points now downward, which means now the force on 2 by 1 is now away from the wires. So we learned from this guy for case 2, so let's call this case 2, is that our forces are now going to be repulsive. So case 2, these guys are going to be repulsive instead of an attractive force. And again, these guys abide by Newton's third law. So regardless of how I look at this, these guys have to abide by Newton's third law. But these two forces are, again, opposite to each other, but these are now attractive, or sorry, repulsive, where in case number 1, they were actually attractive. So putting all this together, we can say then is that the force on 1 by the other one, so our magnetic force between parallel wires, is simply going to be mu naught I1 I2 times the length divided by 2 pi d. And if the currents are in the same direction, this manifests itself as an attractive force. And if they are in opposite directions, then this is equal to a repulsive force. Okay. So this is actually opposite to what we're used to. So we're used to is that what? If we had unlike poles, these guys attract, and if we have like poles, they repel from each other. This is actually the opposite. So if they're in the same direction, they attract, and if they're in opposite directions, they repel each other. So, was okay? Not too bad. So since I'm not on campus, I couldn't make a video of me actually doing this. So I'm going to show you a video that I found. Magnetic fields between two wires. I think what I like most about this video is this is from like the 50s. So it's all in black and white, and it kind of cracks me up watching it, but that's fine. They'll actually show this to you.
To a bus bar up at the top. Currents flow down through these wires, all in the same direction, and out through this copper strap to another bus bar over there. Okay, let's see what happens when we pass current through it. All right, Beans, let's have a little juice here, and let's start gently. Let's have about 1,000 amps to begin with. Takes a minute to fill this all up. Oh, tell them to call me back later. I'm busy. How's it coming, Beans? You got? All right, let's go on up to 2,000. There we begin to go. On up to 3. Let's show it really. Oh, there we go. 4, 5. I
So you
guess
can see the wires
enough.
all attracting each other.
Let's cut it off. Well,
They
I guess
take away
there
the force
isn't
and
any
they snap back
argument about
pretty
which
quickly.
way those forces are working. When currents are moving in the same direction, they attract each other, and you can see that by the squeezing up of this bundle of wire. You've seen what happens when we have currents flowing in the same direction. This time we're going to see what happens when the currents flow in opposite directions. The current comes in from the bus bar through this flexible copper strap, down through this solid copper rod, and back up the other side, and out this flexible copper strap. Now, these are solid copper rods. They don't move easily, and the current on one side goes that way, and on the other side goes this way. Now, let's see what happens.
So for this one, look at the gap between the wires. So right now you see a very small gap.
Time, I want you to set the
Actually, these are copper rods, so they're going to bend only slightly. But
you get the full output of the machine through these all at one crack, and stand by to open it up in case we get any trouble. Okay, let's take it away. Yeah, there it is.
So you can see the gap widening from the repulsive force between these guys.
Rods. There she goes. Whoa!
And then they fried something. So,
okay, fire's on. Did you see the flash out there? That was the circuit breaker that opened the circuit when we were getting too much current through the machine. Okay, go ahead. 500, 1,000, 2,000, 4, 5.
it's burning. There we go. So anyways, so that's the force between parallel wires. So again, when the currents are in the opposite direction, that's a repulsive force. And then if they're in the same direction, then that is an attractive force. So this actually happens in your car and stuff all the time. So when you're driving down the road and you have the radio playing or all kinds of different stuff, and you have wires that are all running to each other, each one of these guys is actually feeling a force. So they're actually either being attracted to each other or repulsed from each other, which is why most of the time you end up using coaxial cables. So what the coaxial cable actually does, as you saw with the prior Ampere's law problem, the group assignment, is that shields the exterior, so it actually cancels the magnetic field on the exterior. So that way you don't actually get forces between wires. But if you're not using coaxial cables, you actually get these forces all the time. So good. So let's do a couple examples. So the first one says that we have a horizontal wire carries a current I1 of 80 amps. A second wire, which is 20 centimeters below it, must carry a current once I know what current I2 does the second wire carry, which is 20 centimeters below, so it doesn't fall under its own weight. And it says that the lower wire has a mass per unit length of 0.2 grams per meter of length. Okay, so let's kind of draw our picture of what's happening here. Good. So we have one wire on top. So here's my wire on top. Okay, this guy is carrying current. I don't know, let's say it's in this direction, I1, which is equal to 80 amps. Okay. Below that, we're going to have a second wire. So this is wire number 1. So wire number 2 is going to be here. Okay. And what we're told is that these two guys are separated by each other by, what was it, 20 centimeters? No, wrong one. There it is. Yeah, 20 centimeters. Good. So these guys are distance D equal to 20 centimeters away from each other. Okay. Now this is happening in a vertical sense, which means that these guys have this one has a gravitational force pulling down on this guy. And we're told that the mass per unit length of this guy, m over L, is then equal to 0.12 grams per meter. Okay. So this is the mass per unit length of this guy. So good. So we want to know then is what is the direction and magnitude of the current in the second wire to make sure that this guy doesn't fall under its gravitational weight. So what we want to do then is levitate wire number 2. Okay. So I want to know what is I2? And again, I want to know what is the magnitude and its direction. So what direction does this guy have to be running to make sure that it doesn't fall under its own gravitational weight? So let's deal with the direction first. So what type of attraction do I want between the two wires? So if this one is down here, we know gravitational force is pulling downward. So what has to be the direction of the magnetic force?
The other wire.
Yeah, it has to be upward, which means that between the two wires, we need to have an attractive force, right? So in this case, are the currents in the same direction or an opposite direction to get an attractive force? Same direction, good. So here we know that I2 has to be in the same direction as I1. Good. Now let's talk about the force. So what's happening here is that this is in a static equilibrium situation, which means the net force acting on our wire has to be equal to 0. So we know the sum of the forces on wire 2 must be equal to 0. So here, let's call the vertical direction the y direction. So we have the sum of the forces in the y direction. So here we have the magnetic force minus the gravitational force, which is simply its weight, mg, must be equal to 0. So this tells us then that the magnetic force must be equal to its weight. Good. Now here, from what we just did, what we know is the magnetic force has to be equal to mu naught times current I1 times current I2 times the length divided by 2 pi d, and that must be all equal to simply mg. Okay. From here, all we have to do now is solve for current I2. So let's do that over here. So from here we get I2 then is equal to, so this is going to be mg divided by mu naught I1 L all times 2 pi d. Right? So this is I2. Now notice I didn't tell you what m was, but I have an m here and an L here, so I can group the m over L as this number here. So I can actually rewrite this then as m divided by L, so that's the mass per unit length, times then 2 pi dg divided by mu naught I1. Okay. So here, m over L is simply 0.12 grams per meter, 2 is simply 2, pi is pi, d is 0.2 meters, g is 9.8 meters per second squared, mu naught is 4 times pi times 10 to the minus 7, I1 here is 80. So plug in my numbers, what I find in this case then is this works out to be 15 amps. So the current I have to run through the second wire must be equal to 15 amps in this case. Let me do enough time. Okay, should have enough time to do the last one. Well, not the last one, but everybody's okay? Not too bad. Let's do another example. So the next one says, so this is number, oh, is that what I want? I want this one, good. So this says we have 4 long straight wires are perpendicular to the page. So each one of these is a wire which is coming out of the page, and their cross-sectional areas form a square where the length between each one of the wires then is 13.5 centimeters. So this is A, where A is 13.5 centimeters, pardon me. And it says each one of these currents carries exactly the same amount of current. of 7.5 amps. So that means I1 here, I2, I3, and I4 all have exactly the same current, which is 7.5 amps. But I'm going to label them I1, I2, I3, and I4 just so we know which one we're actually looking at. And some of them are going into the page and some of them are coming out of the page, which means I1 and I4 are coming out of the page. I2 and I3 are going into the page. So it wants to know, what is the net magnetic field per unit length on the wire on the bottom left? So wire number 4 here. So we want to know, what is the net force on wire number 4? Okay. So good. So let's redraw our situation. Good. So I have wire 1 here, wire 2, well, that's number 4, 2, 3, and 4. So I'm calling this 1, 2, 3, and 4. And then in this case, I got current coming out, current coming out. Here I got current going in, current going in. So this is I1, this is I2, this is I3, this is I4, where we're told that I1 is equal to I2, which is equal to I3, which is equal to I4, which is equal to 7.5 amps. And then the distance between all these guys, A. So A and A, where A is equal to 13.5 centimeters. Good. So ultimately what I want to know in this case then is, what is the force on wire number 4? So this is what we want to know. What's the force on wire number 4? Well, it turns out that the force on each one of these wires then is simply equal to the addition of all of the forces between the pairs of wires. Right? So this is going to abide by our superposition principle, which means the force on wire 1 then is going to be equal to the sum over I of the force on wire 4 by all the other wires. So all we're going to do then is consider the force between each one of the pairs, sum them all together in a vectorial fashion, and then that gives us a total amount of force. So this is then equal to the force on wire 1, or wire 4 by wire 1, plus the force on wire 4 by wire 2, plus the force on wire 3, or sorry, wire 4 by wire 3. And it feels no force from itself, right? So there is no fourth force on this guy. That look like a human being wrote that. There we go. Okay. So good. Now there's 2 ways we can do this problem. One, we can do the long way. We can determine the direction of all the magnetic fields from each one of these, and then use that to determine what is the magnetic field at wire 4 from each, and then use the cross product, point our fingers in the direction of wire of current 4, use our right-hand rules and do all that good stuff. That's one way to do it. The other way we can do it is, we know the directions of the currents, and we know that if they're in the same direction, they're attractive, and if they're in opposite directions, they're repulsive. So that's probably the easier way to do it. Which means that the force on wire 4 by wire number 1 is going to be an attractive force because they are in the same direction. So the force on 4 by 1 points along the y direction. These two between 4 and 3 are going to be a repulsive force because they're in opposite directions. So that means the force on 3 or 4 by 3 is then in the negative x direction. So that guy's going to point that way. So in the negative x direction. And then finally, the force between 4 and 2 is going to point along a 45-degree angle down in this direction. So this is going to be our force on 4 by 2, right? Along a 45-degree line along this direction, again, because these are opposite. So that's going to be a repulsive force. So that means that our total force then is going to point off something like this, right? This is going to be our force on 4 by 1. Or sorry, force on 4 by all the other ones. Okay, so in this case, we should have a total angle here of theta 4, which is then what? Greater than 90 degrees, but less than 180 degrees. Should be somewhere in that ballpark. Okay. Good. So this way we can do it one of 2 ways. We can either use unit vector analysis, or we can just do component form. I think the way I wrote the answer was in component form, so let's use component form. So let's do it that way. So good. So what we can do in this case then is break this up into components. So we can look at just the x portion, and we can look at just the y portion of the net force acting on this guy. So in the x direction, we have what? This portion here, which is actually going to be in the negative x direction. And we have all of this force. So this is going to be the force on 4/3. We have all of that guy. And then from the force on 4/2, we have just the cosine component because this is simply equal to 45 degrees. So this is going to be plus force on 4/2 times cosine of 45 degrees. Okay. Here I'm dropping the negative sign because I'm writing a component. I'll put the negative sign in there as well. That's going to be a negative. They're both negative. In the y direction, we now have what? All of F41, right? So we have F41 then is going to be all in the positive y direction. And then here we have, this is pointing down in the negative y direction. So we get a minus F42 times sine of 45 degrees, right? Because we want only the vertical component of that. Everybody's okay? So let's write down each one of these. So this becomes minus. Now they all have a mu naught I, right? Because they all have, let's call that I4, all in common. They all have the same length, so we get times L, and then we're left with what? I3 divided by, let's pull out the 2 pi because that's all the same too. So let's call this distance then R43 plus I2 divided by R42 times cosine of 45 degrees. So that's this guy. And then this one is going to be equal to, so now I get a mu naught I4, let me hide that for a second, times L divided by 2 pi times, so here I'm going to get an I1 divided by R41 minus I2 divided by R42 times sine of 45 degrees. Looks like I'm over in time. That's great. So last thing is, so what are each one of these distances? So this distance is what? R41. This distance here is R42. And this distance here is R43, which means R41 is equal to R43, which is simply equal to A. And then R42 is then this distance across here, which is then the square root of 2 times A. So R42 then is the square root of 2 times A. Finally, also using then I1 is equal to I2, which is equal to I3, which is equal to I4, which is equal to that. We plug in our numbers. We get in this case then is, now again, we're looking for the force per unit length. Since we don't know what the length is, I'm simply going to divide both sides by the length and write these as the force per unit length. Okay. So plug in my numbers. What I get in this case then is, let me switch to another page real quick. So we get the x component is then equal to negative 1.25 times 10 to the minus 4. And this has units of newtons per meter. And then we find that F4y is then equal to 4.17 times 10 to the minus 5 newtons per meter, which means the angle then, theta 4, is the inverse tangent of these guys. So again, an F4y divided by an F4x, which works out to be like 166 degrees, somewhere around there. I have it written on the slide. This one, 161.55. So 161.55 degrees. All right. There we go. All right. So next time, so tomorrow, we'll do one more example. So in this case, we'll put something in a magnetic field of a solenoid. So we'll do one more example with a solenoid. And then after that, I have a group assignment for you. So we'll let you do the group assignments. And then after that, we'll start the next chapter, chapter 30, right? So next chapter gets a little weird. So basically, we'll find out there is a connection between electric fields and magnetic fields. So far, we haven't seen a connection between them. So that will actually tell us those. Can I go back to one slide? Sure, Dylan, I would love to. So which slide do you want me to go back to? Let me share my screen again. This slide, Dylan, or a different one?
The one that had the work, so the one before that, I think.
All this stuff? Okay.
Oh, thank you.
You're welcome. Sorry about that. I was pressed with time, trying to go a little fast. So everything's okay. So like I said, so tomorrow we'll do one more problem. Then I'll give you guys a group assignment, and then we'll start chapter 30. And then that'll be great. Okay. You're welcome, Dylan. Okay. So anybody have any questions or anything? He's doing okay? Not too bad.
So with the dot and the cross thing,
Yes.
Where do you get that from?
The dot and you mean on the pictures, or the dot product and the cross product? So which dot and cross are you referring to?
The product.
Oh, okay. So what's the difference between them, or just where are they coming from?
Like, how do you know to use them instead of like the normal multiplication sign?
Oh, okay. So that'll come from the definition of the objects that we're doing. So for example, so let me share my screen again. Share. Good. So those will come from the definition of the object at which we're using. So for example, when we're talking about Ampere's law here, Ampere's law is defined specifically in terms of a dot product. So in that case, from its definition, what this says then is we're only taking the portion of the magnetic field which is parallel to DL. That's what this thing is saying. So these two things have to be in the same direction, otherwise they're going to be perpendicular to each other. And then when we're talking about the forces here, the forces are specifically defined in terms of the cross product. So determining which one I use will come from the definition of the object that I'm looking at. So when I'm talking about the magnetic forces, both of those have cross products. If I was talking about the torque on a magnetic wire, for example, that's mu naught crossed by external magnetic field. So this is also a cross product. If I'm talking about the energy, this is minus mu dotted with the magnetic field. So each one will be dependent on how the object is actually defined. So in the definition will come if this thing is a cross product or a dot product. Okay, is that kind of helpful?
Yeah, and then which one's which? Is the cross the cosine, or is the cross product?
Cross is always with the sign. So the magnitude of this guy would then be equal to mu times b times sine of the angle. And then the dot product is minus mu times b times cosine of the angle. So just remember that cosine means two things are parallel, and then cross products means two things are perpendicular. So to cause a torque onto something, I have to push on it in a perpendicular fashion to get it to rotate. But to move an object, I have to move it. I have to put a force parallel to the direction in which I want to move it. Okay, so it's probably easier to think about it that way. So anytime I want something to feel a force in a direction opposite to the direction in which it's going, it has to push on a force tangential or perpendicular to that object. Okay, so that's right. So cross product always goes with sine, and dot product always goes with cosine.
Thank you.
You're welcome. Any other questions anybody has?
Yeah, in the equation for the magnetic field right there, what's the, is that a DL cross R hat?
Yeah, that was a lame attempt at, I started writing something else.
Okay.
So, yes, so that's a, oops. Yeah, so that is a DL vector crossed by R hat. Yes, yeah. And that's a half written pi down here. So. Making fun of my handwriting. Okay. Okay. Any other questions anybody has? Everybody's good? Okay. All right. So otherwise, I'll see everybody tomorrow for more exciting physics to talk about. It will be great. Bye, everybody.